Good morning. So this is it, the last presentation of the year. This one's going to be covering acids and bases. We'll finish off our equilibrium unit. The first thing we're going to look at are the properties of acids and bases. So this is going to be, for the most part, a qualitative description. In terms of tastes, acids are going to be sour. A lot of foods have a sour taste to them. Most of your citrus fruits will have a sour taste. Vinegar would be another example. Ascorbic acid, which is vitamin C found in orange juice, again is a acidic substance as well. As far as your bases are concerned, they will taste bitter. Most of the time we don't eat very many bitter foods, but some types of like the unsweetened chocolate can be a slightly basic food as well. Soap is a type of base. So if you have ever had your mouth washed out with soap, you know it's not a pleasant taste. When we talk about bases also, as far as their touch is concerned, they feel very slimy. So if you ever get a very strong detergent on your skin and you just kind of rub your fingers together, you can see that it is very slimy. The stronger concentrations for the solution can cause you to have irritated skin. Acids are going to feel very much the same as water, except that if you get an acid on you, it will burn your skin if it's a concentrated solution. The dilute solution, if you ever had like lemon juice in a cut on your finger or vinegar on your finger, something like that, on broken skin, it can sting a little bit, but it won't give you a chemical burn. The next property that we're going to look at are the reactivity with metals. For acids, they will react vigorously with active metals. I'm going to put that up here. And they will always produce hydrogen gas, which is the H2, and a salt. So you have, in this case, the hydrogen being replaced by the magnesium, producing the hydrochloric acid and the magnesium chloride as your salt. Please remember, when we're dealing with that active metal concept, we are referring to the activity series. So if you recall with our activity series, if a metal that is by itself is higher on the activity series than the element that it would switch places with of the same charge in the compound, then the reaction will take place. So only the metals that are above hydrogen on that activity series would actually react with the acids. Anything below, I've referenced the fact that I could put my gold ring into the hydrochloric acid and absolutely nothing will take place. So it has to have the metals being above hydrogen on the activity series. For your bases, they will not react with metals at all. The next property that we deal with will be electrical conductivity. For your acids and bases, they are both electrolytes. So that means that both solutions will conduct electricity. Now, there is one big thing here. When we talk about your strong acids and bases, and we'll get to those a little bit later, those will be strong electrolytes. We've already talked about this in our solutions unit. And that's strong acids and bases. And then our weak acids, those will be weak electrolytes. So although they will conduct a current, it will not conduct as well. So you'll get a slight bit of current that will flow through. The last property we're going to look at are the reactions that are occurring between acids and bases. So typically when we react an acid with a base, we would always form a salt and water. So when we look at these types of reactions, we use something that we call an indicator. An indicator is going to be a weak acid system that will change colors when it's exposed to different pH levels. You can kind of think about this part here where it's changing colors as being an example for that common ion effect when you are dealing with Le Chatelier's principle. The additional acid or base from our reaction will be supplying the extra hydrogen ions or hydroxide ions into the indicator, which will then cause it to shift from one direction to the other, which will cause a change in colors. The most common one that you guys have probably used before your chemistry back in your biology class was litmus paper. You guys would probably remember that when you take blue litmus paper and you stick it into an acid, the paper will turn from blue to red. So acids will turn red. Bases, when you take red litmus paper and place them in solution, the paper will turn from red to blue. So bases turn blue, so just remember that the B's go together. Bases turn blue, and the acids will turn red. We have many different natural indicators that are in our environment. If you guys at your house have any hydrangeas, that is a natural indicator that we have that changes colors based on the pH of the soil. If I remember correctly, typically in an acidic environment, the hydrangeas will have a blue color, and in a basic environment, they will have a pink color. So I know when I first bought my hydrangea for my yard, I had a pink one, and within a couple of years, due to the acidity of the Georgia soil, it turned from a pink to a blue. There are also green peppers that are another example of a natural indicator. If you change the soil types for some of the different peppers, the peppers that will grow will actually turn out to be different colors. I had a kid do a science fair project on that a few years back, and it was a really cool project. When we talk about this acid-base reaction, again, this is called a neutralization reaction. And then finally, just one extra one, which I hope would make sense as part of this, is that bases will break down proteins. Your protein structure, they're made up of amino acids, so we just have a neutralization reaction. The amino acid reacts with the base, and it will form something else. It will denature it, is what they call it. We're now going to look at the different models for acids and bases. The first model that we're going to look at is called the Arrhenius model. Svante Arrhenius was a Swedish chemist who won a Nobel Prize for his work in kinetics back in the 1880s. He defined an acid as a substance that when dissolved in water would produce hydrogen ions, and a base was a substance that when dissolved in water would produce hydroxide ions. This is the most limited version of acid and bases that we have. The second model was presented by two different scientists, Bronsted and Lowry. So we call this the Bronsted-Lowry definition of acids and bases. They came up with acids as being substances that will donate a hydrogen ion, which we call a proton. Bases are proton acceptors. From our work back in the fall, you'll remember hopefully that if we're talking about a neutral atom of hydrogen, it would possess one proton, 0 neutrons, and 1 electron. If we go to a hydrogen ion, mass number, atomic number stay the same, but now we have lost an electron. So by removing that 1 electron to get that positive charge, you'll notice literally all we have left is just a proton. So we define that acid or base based on whether or not they are accepting or giving away a hydrogen ion. The last definition that we have is what we call a Lewis acid. This is one that we're not going to cover in honors chemistry, and you won't even really cover it in AP chemistry. So I just want to take a brief moment to describe what it is so that the first time you see it is not in college. So for your Lewis acids, that is going to be a substance that will accept an electron pair. So a substance that accepts an electron pair. You can think about these as being electron deficient molecules. And then we have a Lewis base as something that has a very large number of electrons. So this is going to be a substance that donates an electron pair. So an example for something like this would be NH3 with its structure. Again, it has the 2 lone pair electrons on the top. So it has this. We could have something like BF3 as an example for a Lewis acid. Again, notice here the boron only has 6 total electrons around it instead of 8. So it can take these 2 lone pairs electrons from the nitrogen and form a coordinate covalent bond with the boron, and you'd have a new compound that would form. So the Lewis acid, the substance that would accept the electron pair, again, it's electron deficient. The Lewis base is a substance that donates the electron pair, and it is something that will give away its 2 electrons. Instead of sharing 1 electron each to form a bond, it will donate both of the electrons to form a bond with the boron. So we're now going to focus on the ionization of an acid in water. We're going to start off with this first one being a monoprotic acid. So this one is still going to follow the Bronsted-Lowry definition of our acids and bases. You can see very clearly here in this picture, we have our acid, the small circle, that would be the hydrogen, and this would be whatever the anion is in the purple. I have water, again, H2O. It's going to form H3O plus, and then the A minus here. So the first thing we need to do is just define for a moment what the conjugate acid and the conjugate base are. So these are always paired together. So you'd have one acid on one side with one base, because when it goes in the reverse direction, it's going to be performing the opposite process. So the conjugate base is going to be the substance that will remain when the acid has lost the proton. So by splitting up this acid here, giving this hydrogen to the water, I would be left with the A minus. The conjugate acid is going to be the substance formed when the conjugate base accepts a proton. So when this happens, I went from H2O to now H3O plus. So the water added the extra hydrogen, forming the H3O plus. So we would have our conjugate acid linked together with our base. We would have our conjugate base linked together with the acid. Just a reminder, a little helpful hint, the conjugate base on the product side, product will always have one more hydrogen ion. The conjugate acid, the product will always have one less hydrogen ion. Now, when we look at these examples, this can happen for bases as well, but we're going to focus on acids to begin with. And we're going to look at acids that can donate more than one hydrogen ion. We're now going to look at polyprotic acids. So that term poly means many. The protic is talking about protons. So that's talking about the hydrogen ions. And so when we talk about polyprotic acids, that means that they can donate more than one hydrogen ion per molecule. You've got to be careful, because we have different types of acids where it could appear that they have more than one hydrogen, but they actually don't. So when we talk about those organic molecules, such as acetic acid, where we have CH3COOH, the only acids, or the only hydrogens that can ionize, are ones that are bonded to the hydrogen. So acetic acid would be a monoprotic acid. These 3 hydrogens here, they're attached to the carbon as part of that organic molecule. They do not ionize. So this is the only one. Now, as I said, these acids can ionize one hydrogen at a time. So if I have a diprotic acid, that is going to be a substance that can donate 2 hydrogen ions per molecule, but it's going to occur in 2 separate steps. So our first ionization would be for carbonic acid, as an example, H2CO3. We could take this, reacting it with water, just to make it that Bronsted-Lowry definition, forming H3O plus and the HCO3 minus. Don't get confused if you see it in this type of format. H plus and H3O plus are synonymous with each other. The hydrogen ion, because it literally is just a proton, it will bond with anything that has lone pair electrons in solution, so you'll never really find the H plus by itself. So you could have these two things interchanged. I could add in the water here, put in the H3O plus instead, and it would do the same thing. So if you notice here, the conjugate base that we had for this first step, the HCO3 minus, it's now going to undergo a second ionization because it has that ionizable hydrogen here, react with another water molecule, forming an H3O plus, and then we'd have a CO32 minus that would be left in solution overall. So your total balanced equation, you would have the H2CO3, you would have two H2Os, they would form two H3O plus and CO3 2 minus. That would be your overall reaction, but it happens in multiple steps. If I have a triprotic acid, that means that I have an acid that can donate 3 hydrogen ions per molecule, and it would now occur in 3 steps instead of 1 or 2. So you can see here with the example of phosphoric acid, it's going to take the original H3PO4, forming an H plus, and then the H2PO4 minus. So hopefully you can see the H2PO4 had 1 hydrogen removed away from it. And now it's going to become the acid in the second step. So the H2PO4, it comes over here. It's going to lose a hydrogen to form the HPO4 minus, and then that will or 2 minus, and that will finally go through one last ionization step where it will form the H plus and the PO43 minus. Now, the one thing I just want to tell you is that the extent, because this is getting into equilibrium, notice the double-sided arrows. As you get past the first ionization step, the second and third steps will occur to a much smaller extent. So we're going to revisit that example that we just talked about. If you notice here, we are looking at the acid ionizing in water. So we have our monoprotic acid, hydrochloric acid. The hydrogen from the HCl molecule is going to transfer over to the water molecule. This is going to make the water act as the Bronsted base. Now, when we have a substance that has the ability to both accept and donate a hydrogen, we call that an amphoteric or amphoprotic substance. So that's going to be a substance that can act as either an acid or a base. If we look at something like ammonia reacting with water, when these react together, it'll form NH4 plus and OH minus. So when we look at this, notice the NH3 went to NH4 plus, so that makes it the Bronsted base because it accepted a hydrogen. The water went from H2O to now OH minus, so it lost a hydrogen. That makes it the Bronsted acid. The NH3 goes to the NH4 plus, so again the substance formed when the Bronsted base accepts a proton, that's the conjugate acid, and then the conjugate base, the substance remaining when the Bronsted acid donates a hydrogen. So that term amphoprotic, you've seen it here where hydrogen is added to the water, making the water the Bronsted base. And then you've also seen down here now where the water can act as the acid and give away its hydrogen. We're now going to look at a few examples of some acid-base pairs. Remember, when we react the acid and the base, we'll get the acid from the reactants pairing up with the base from the products. So there's our conjugate acid-base pair. And then the base from the reactants goes to the acid for the products. And that would be your other conjugate pair. So when we look at our first reaction, we have HF plus H2O, and it's going to form F minus and H3O plus. So again, you notice the hydrogen left the HF molecule, leaving it as the F minus. So therefore, when this happens, we know that the acid would be the HF, the base would be the water. And then this would be my conjugate base and my conjugate acid. For our second reaction, we have formic acid, HCOOH, plus Cn minus. So this is going to be a little bit different variation, but you'll notice when we do this that we form HCOO minus plus HCN. This Cn minus, the cyanide ion, is coming from some type of salt. So that again is where we can use a little bit more of a broad definition for our acids and bases. Because the Cn minus is reacting with a hydrogen and forming the HCN, it is increasing the concentration of the OH minus in the solution, and it's also accepting a hydrogen. So as a result of that, it would be our base, and then the HCOOH is our acid. So here's another example of one of those organic molecules where we have just one hydrogen. It is this hydrogen that ionizes, not the one attached to the carbon. So that would be your acid-base pairing yet again. As we look at our next example, we have NH4 plus CO3 minus. When these two things react together, it is going to form NH3 and HCO3 minus. So in this case, the NH4 plus, that is our acid. The CO3 minus, the carbonate ion, if you notice, it is accepting the hydrogen, so it is our base. The H2PO4 minus plus a OH minus, forming HPO4 2 minus and H2O. So in this case, the hydrogen from the H2PO4 minus going to the hydroxide, forming water, leaving you with the HPO4 2 minus. We have H2SO4 plus N2H5 plus. When these react, it's going to form HSO4 minus and a complex ion N2H6 with a 2 plus charge. You'll notice again though, the H2SO4 donated its hydrogen to the N2H5 plus, so that would again make the N2H5 plus your base. And our final reaction, HPO4 2 minus plus SO3 2 minus. This is the one where you got to use a little bit of common sense because there's no other option here for the base other than the SO3 2 minus, because it doesn't have a hydrogen already present. It's got to accept one. So we know our products are going to be PO4 3 minus and the bisulfite ion HSO3 minus. Okay, so let's do a little quick concept check, and let's try to find a pair of compounds that would represent a conjugate acid-base pair. Now, when we talk about that conjugate acid-base pair, we're talking about the Bronsted acid being linked up with a conjugate base, or the Bronsted base being paired up with its conjugate acid. Remember the key thing? We can only lose one hydrogen per stage or per step. So when we look at our first one, I have two acids, HCl, HNO3, hydrochloric and nitric acid. That will not work. I have H3O plus and OH minus. That could potentially work, except for the fact that there's more than one hydrogen difference between them. So both of those cannot be it. Same thing for C. H2SO4 and SO4 2 minus, those lost two hydrogens, so they cannot be conjugate acid-base pairs. And finally, HCN with Cn minus, we are only losing one hydrogen, so that would be our correct answer. Next, we are going to discuss acid strength. Please do not confuse acid strength with concentration. I can have a strong acid that has only 1 times 10 to the minus 5th moles in it, but it would still be classified as a strong acid. And I could have a weak acid with a concentration of 20 molar, and it would still be considered a weak acid. So when we talk about the acid strength, we're talking about how much the acid will ionize or dissociate in solution. So we call that the extent to which it ionizes. This is our precursor to equilibrium. When we talk about strong acids, a strong acid is going to be a substance that will completely ionize or dissociate. Those two terms are essentially interchangeable. And so therefore the equilibrium position will lie far to the right. So you'll essentially have no equilibrium because all the molecules will convert into the conjugate acid and the conjugate base. You can see here with the picture on the left side, notice how all the acid molecules are together, and then as they go to the product, they have all separated into H plus and A minus ions in the solution. So I have no HA left over at the end. When I look at a weak acid, it is one that is only going to partially ionize, as we have talked about before. So when we talk about these, we would still find that the equilibrium will now lie far to the left for the most part, and I will have mostly the acid molecules staying together in solution. So if you notice here at the start, all of my acid molecules are together. When I look at the product side, I have just a few that have actually split apart or ionized. The rest of them remain together as that acid molecule. So again, think products over reactants. Most of the molecules stay intact, so I have a large reactant concentration versus a very small product concentration. So you're going to find your Kas are going to be very small, much less than 1 the vast majority of the time. We have 6 strong acids that you guys need to memorize. Your list of strong acids. We have the hydrohalix, HCl, HBr, HI. We have our polyprotic acids, which would be the H2SO4. And then we have our last 2 oxyacids, ones involving polyatomic ions, HNO3 and HClO4. These are the 6 that are recognized by College Board as being strong acids, so those are going to be the ones that we will recognize for class. Any other acid would be classified as a weak acid. So here's a little table that describes the acid strength in a number of different ways. The first of which is the Ka value. Just remember, when you see Ka or Kb, that's just talking about the acid or the base that is going to ionize or dissociate. Typically we talk about acids ionizing, bases dissociating, and it's just the type of compounds that they are to start off with. Since bases are metal hydroxides, they're typically an ionic compound, so they're going to dissociate. The acid being a polar molecule, it will ionize. Not a big deal, use them interchangeably, nothing to worry about. So for your strong acids or strong bases, you have your Ka being very large, so we have mostly products, so it's lying very far to the right on the equilibrium. And so as a result, your hydrogen ion concentration will essentially be the same as whatever the concentration of your acid happens to be originally. And then finally, the strength of your conjugate base compared to the water acting as a base will be much weaker as a result. So when we talk about the weak acids, your Ka is going to be very small, so the equilibrium position will lie far to the left. So again, talking about much smaller than 1, which tells us that at equilibrium, you have your H plus concentration being much smaller than your HA concentration. Typically, we're talking about less than 5% in most cases. And then in this situation, your conjugate base is going to be a much stronger base than the water is. So I just want to take a moment to kind of focus on that for just a moment. So we look at a typical type of weak acid. So I'm just going to pick one here, and let's just say that I give you something like HClO. So I have hypochlorous acid, and when that goes into water, it is going to form H3O plus and ClO minus. Now, the Ka for this reaction is somewhere roughly around 2 times 10 to the minus 8th power. So if you notice with that being such a small value, that means that the reaction is going to occur in the forward direction to just a very tiny amount when equilibrium gets established. So I'd have a large amount of the HClO in solution. I'd have a very small amount of the products that would form. So you kind of think about this as just like a tug of war competition. When we look at this in the forward direction, again, the H2O is acting as the Bronsted base. The HClO is acting as the Bronsted acid. The H3O plus, that's my conjugate acid. The ClO minus is my conjugate base. Now, since I have a large percentage of the HClO found in solution, that means when all these things get mixed together, as soon as an H3O molecule comes in contact with that ClO molecule, it's going to revert back to form the products. So therefore, this compared to the water would be a much stronger base. And I know that because the K value is less than 1. So we're now going to look at water acting as an acid and as a base. When we do this, again, we talk about the water being amphoteric. It is not the only substance that is amphoteric, but just the most common one that we use. So it can act as either an acid or a base. When we are at 25 degrees Celsius, we can look at a new equilibrium concept called the autoionization of water. So when I look at two water molecules, H2O and H2O, reacting together, they're going to form H3O plus and OH minus. Again, these two being liquids, these two being aqueous. So if we were to set up our equilibrium expression, we'd have Kw equals H3O plus times OH minus. You can see in this case the hydrogen here could be given to this water. So I'd have my Bronsted acid, my Bronsted base, conjugate acid, conjugate base. Now, the significance of this is that the new equilibrium expression, that Kw, always has a value of 1 times 10 to the negative 14th power at 25 degrees Celsius. Remember, this is temperature dependent. So this is going to be the first big mathematical relationship that we're going to have when we're dealing with acids and bases. So for this expression, we can look at the concentration of the H plus times the concentration of the OH minus. Think about Le Chatelier's principle. If one of these two concentrations changes, it's going to affect the other one as it shifts in a certain direction. So no matter what we do, the product of the H3O plus and the OH minus together will always equal 1 times 10 to the minus 14th. So now if we look at the H3O plus compared to the OH minus, if I have a solution where I can see that the H3O plus is greater than the OH minus, and I can do that by dividing into that Kw, so 1 times 10 to the minus 14th divided by a concentration. If the H3O plus is greater than OH minus, meaning I have more hydrogen ions than hydroxides, then my solution is going to be acidic. If I have equal amounts of H3O plus and OH minus, then that means that I have a neutral solution. And if I have a larger amount of OH minus than H3O plus, again that hydronium ion, then I will have a basic solution. Okay, so let's talk about the equations that we can use when we are calculating pH. So I have a little handy flow chart here that you guys can use. The first thing I want to stress to you guys is that there's no one correct way to solve the problem. As you can see, with it being a nice little square here, you can go in either direction. It's just that one side is going to be a little bit more difficult than the other. So when we talk about our pH equations, we can solve for pH, which would be the negative log of the H3O plus. So again, that's going to be your difference between the pH and the H plus. So if we want to go in the reverse, where we're given the pH, but we don't have the concentration, if we take the inverse of the log, that is 10 to the negative pH equals the H3O plus concentration. It works the same way. The POH is simply the negative log of the OH minus concentration instead. And if we want to find the OH minus from the POH, then we would just simply take 10 to the negative POH, and that'll tell us the OH minus. If we have the H plus or OH minus and we want to solve for the other, it is quite simple. We just take that KW equation and we have H3O plus times OH minus. So I can always use that KW formula, 1 times 10 to the minus 14th, and I can just simply divide by the OH minus to solve for H plus, or divide by H plus to solve for the OH minus. But again, KW always equal to 1 times 10 to the minus 14th. Now, from your properties of logs on the other side, if I want to go between pH and POH, this is a little bit more complicated. So from your properties of logs, if I take the negative log of the entire KW expression, where I have H3O plus times OH minus, if I take the negative log of the whole thing, that gives me negative log of the KW equals negative log of the H3O plus the negative log of the OH minus. So the KW always having that value of 1 times 10 to the minus 14th. If I take the negative log of 1 times 10 to the minus 14th, that is equal to 14. So if you've ever wondered why the pH scale ranges between 0 and 14 typically, or 1 and 14 from what you guys typically have heard, it's because of that KW always equaling 1 times 10 to the minus 14th at 25 degrees Celsius. So that's my negative log of the KW, and I can set that equal to the negative log of the H3O plus, which by definition is your pH. So I could have 14 equals pH plus negative log of OH minus, which by definition is POH. So just like the H3O plus and the OH minus have to be multiplied together to have it equal 1 times 10 to the minus 14th, we can take the pH, add the POH, and it will always equal 14. We're now going to do a quick little concept check, and we want to see in the context of an acidic solution which one of the following statements would be correct. So again, if we have an acidic solution, that means that I have to have a greater amount than the hydroxide ions. So if I look at this first one and it says H plus is less than 1 times 10 to the minus 7th, that means that my hydroxide, in order for it to be equal to 1 times 10 to the minus 14th, would have to be greater than 10 to the minus 7th, which means that that would make a basic solution. So A is not one of our choices. For B, we have H plus being greater than 10 to the minus 7th. If it's greater than 1 times 10 to the minus 7th, then the OH minus would have to be less than 1 times 10 to the minus 7th. So that is correct. The OH minus being greater than the 10 to the minus 7th, that's going to be the same thing as A. So I would know that the H plus would be less than 1 times 10 to the minus 7th. So C would not be the choice. And then H plus less than OH minus, that obviously is not the correct choice either. So B would be your correct answer. All right, so now let's actually look at a math problem to determine the hydrogen concentration and the nature of the solution. So once more, we have our equation, Kw equals H3O plus or H plus times the OH minus concentration. We know Kw, 1 times 10 to the minus 14th. We can divide that by the given concentration, 2.0 times 10 to the minus 10th, and that will equal the concentration of the H3O plus. So if I take 1 times 10 to the minus 14th divided by 2 times 10 to the minus 10th, 1 divided by 2, that would be 0.5 times 10 to the 14 minus 10, or negative 14 minus negative 10. So that would be a negative fourth. We need to shift that over one more spot. So we'd have 5 times 10 to the negative fifth molar H3O plus, which would make it acidic because the concentration 5 times 10 to the minus fifth larger than 2 times 10 to the minus 10th. So the answer would be C. So we're now going to look at the pH scale. So just understand to begin with that the pH scale is a relative scale. It provides us with a convenient way to look at concentrations of the hydrogen ions in solution and make it workable numbers. So when we talk about the pH, the definition of pH is taking the negative log of the H plus. So basically it's standing for hydrogen power. So hydrogen raised to a power. So this is going to be our first time where we're looking at logarithms. Now, I know many of you guys have worked with logs in your math classes at this point, but just in case you haven't, the log is, in this case, only going to be base 10. So what we want to do is see what we would have to do to raise 10 to a certain power in order for it to equal a number. So anytime that you see that P in front of something, pH, POH, PKW, PKA, PKB, it always stands for the negative log. So just as a quick example, if you've never seen anything with logarithms before, if I have a number that is 1,000, we're essentially trying to see what power I would have to raise 10 to in order for it to equal 1,000. So in this case, the x would equal 3. So if I have the negative log for a number, again, I'm going to take, say, 0.001. Log of 0.001, 10 to the x would equal 0.001. So my x would equal negative 3. And then because of the negative sign out in front, that would change it into a positive 3. So when we talk about the pH scale, it is kind of inversely related to what you would think. As the strength of the acid increases, again, the H plus is increasing, the pH is going to decrease. Typically, the pH is going to run between 0 and 14. The lower the pH value is, the more acidic the solution would be. So the higher concentration of H plus. When we look at the OH minus concentration, the more acidic it gets, the smaller the amount of OH minus is in the solution. And then when we have your basic solutions, again, you'd have a greater amount of OH minus, so we'd have a smaller amount of H plus, so therefore the amount for the pH would increase. So you can see that graphically with this data table here. We also have the POH. The POH would just be the negative log of the OH minus ion concentration instead. The last thing that we have to do is dealing with significant figures. So when we are dealing with pH, the number of decimal places in the logarithm is equal to the number of significant figures in the original number. So the first number that you see, and I'm just going to look at this first example, the 15 here correlates to the power to which 10 is raised. This part here just shows decimal placement, which by our normal rules of significant figures means that it is not significant. This number here corresponds to the 15 in the pH. The number out in front that's underlined, the 1.0, that correlates to the number of decimal places that I will use for my pH. Since the 1.0 has two significant figures, I place 2 digits after the decimal point. So when I write 15.00, that will have 2 significant figures. Now, calculating the pHs for solutions is actually not too hard. You just got to use a little bit of logic. If you have solutions where your concentration is 1 times 10 to some power, anytime that I take that, negative log of 1 times 10 to the minus 4th, you don't even have to plug it into your calculator. Whatever your exponent is for the 10, that's going to be your pH. So in this case, if I took pH negative log of 1 times 10 to the minus 4th, the pH would equal 4. Now, for the next set, it's a little bit more difficult, but you can use, especially for multiple choice questions, you can use a little bit of logic. If I were to look at the pH scale, so I'm just going to draw this over here. So here's my pH scale, here's my pH, here's my H plus concentration. So if I were looking at this, and here's my pH of 1, here's my pH of 2, here's my pH of 3. In terms of the hydrogen ion concentration, this would be 1 times 10 to the minus 1. This would be 1 times 10 to the minus 2. pH of 3, 1 times 10 to the minus 3. So when I look at this number, 0.040, if I were to write that into scientific notation, I would have 4 times 10 to the minus 2. Now, if I were to try to get all of these numbers to have the same exact exponent, since this is a minus 3, if I want to make that a minus 2, I would need to shift my decimal point 1 spot to the left. So I'd have 0.1 times 10 to the minus 2. With the pH of 1, because that's a negative 1 for that concentration, I'm going to shift the decimal over to the right 1 spot. So I could rewrite that as 10 to the minus 2. Now, all of my exponents are the same. So when I look at this and I see that my number out in front is a 4, that's going to tell me that it's going to fall somewhere between 1 times 10 to the minus 2 and 10 to the minus 2, because it is in between with the front numbers. So I know as a result with 4 times 10 to the minus 2 that my pH is going to be somewhere between 1 and 2. So now all I have to do, take the negative log, 4 times 10 to the minus 2, and you end up with a pH equal to 1.40. 2 significant figures here, 2 significant figures here. Okay. So technically I should put 4.00 on the first one. So for our next problem, we're going to go in reverse. We're going to take the initial pH of the solution and figure out what the H plus concentration is. So when we talk about the inverse for the logarithms, we take 10 and we raise it to a certain power, in this case the pH. And taking 10, raising it to the negative pH, that will equal your H3O or the H plus concentration. And so when I look at this, I'm going to take 10 raised to the negative 5.85. Since 5.85 has 2 digits after the decimal point, my answer is going to have 2 significant figures. So if I take the second log for 10 raised to a power, negative 5.85, that will give me 1.4 times 10 to the negative 6th power. And that is your molarity of H+. So next we're going to solve for the pOH of a solution. So you'll notice in this first problem we have the concentration of H+ given, but we know pOH is the negative log of the OH- concentration. So we have a slight problem here. We need to get from H+ to OH-. Now we have a couple of different options. Looking back at our little chart for these problems, I can take the H+, convert it into OH- using that KW formula, and then using your negative log of the OH- forming the pOH, or I could simply take the H+, using your negative log formula, convert to pH, and then from there, using your 14 minus pH, determining the pOH. I'm going to do this first problem, both methods, so that you can see it being done, but again, you can choose whichever one you want. So when we look at this first one, if I take the negative log of 1 times 10 to the minus 4th, we know that the pH would be equal to 4.00, and then I could simply take 14 minus the pH, which is 4.00, and we end up with 10.00 for the pOH. The other method that we could use, as I said, we could take our KW value and divide it by the concentration of the H3O+. So I could have 1 times 10 to the minus 14th divided by 1 times 10 to the minus 4, which is equal to 1 times 10 to the minus 10th. And then I could take the negative log of 1 times 10 to the minus 10th, which would equal 10.00. So either way, you still end up with a pOH equal to 10. When I look at my next problem, I have for this one, negative log of the OH- concentration, two significant figures here, so therefore I just plug that in and we get the pOH equal to 1.40. We're now going to begin looking at setting up our acid-base equilibria. Please recall that your strong acids will dissociate completely or ionize completely in water. So pay attention, please. That means that you're going to have a single arrow. That arrow again means that it has gone to completion, and so you'll have no more HA left in solution. Now, when this occurs, notice here you can have the HA. It can be a gas, it can be a liquid, it can be aqueous. The water is always a liquid, but there will be no equilibrium. So for your strong acids, you would just simply take the negative log of that HA concentration that you had initially, because that is again equal to the negative log of your H+. When we talk about your weak acids, they are only going to partially dissociate. So when we look at those, we have a double-sided arrow to signify equilibrium reaction once again. And we have a small amount of H3O+ and A- that forms, and have a large amount of HA that would be found in solution. So when we discuss this, the Kc value would be much less than 1. The Kc for a strong acid again is much greater than 1. So we're talking 10 to the 8th or greater for the strong acids. You're talking typically most of the time around at least 10 to the negative 4th or smaller for your majority of weak acids. When we set up the equilibrium expression, it's still the same thing, products over reactants, but now instead of using Kc, we're going to use the Ka. Remember, whenever we have equilibrium reactions, if I have a liquid or a solid, they get excluded. So the Kc would get multiplied by the H2O concentration, and that's going to give us our new constant, the Ka. And that's going to be set up and equal to the H3O plus times the A minus divided by the HA. Remember, the stronger the acid is, the higher the H3O plus concentration will be. Larger number in the numerator, that would also mean that I have a larger amount of A minus that would form as well. So I'm going to put that here in addition. And so as a result, because I have more product compared to the reactants, I'm going to have a larger value for Ka. It's still going to be less than 1, but it's just larger than some of the other components. So again, stronger the acid is, greater extent to which it dissociates, the larger the value for the Ka will be. So every time that we have a weak acid or a weak base being dissolved in water, we have two competing equilibrium systems that are taking place. We have the one between the acid itself and the one between the different water molecules. Whichever substance will produce the largest amount of H3O plus or OH minus, that is going to be the reaction that will predominate and control what's taking place in solution. So when I look at this and I have a Ka of 6.2 times 10 to the minus 10th versus a Kw of 1 times 10 to the minus 14th, each one of these would be an X that would be equivalent to each other. And so if I were to take the Ka and set this up, I would know that the Ka for this particular reaction is going to have an H plus concentration greater than 1 times 10 to the minus 7th power, which is what the H plus concentration in the bottom reaction would be equal to. So as a result, because this is a larger concentration, that is going to shift the water reaction more towards the left and lower the concentration of the OH minus. So in this particular reaction, the HCN would control the pH. Now we're going to actually figure out how to calculate the pH for a weak acid. Unlike the strong acids, where we can typically look at the concentration initially of the parent acid and use that as a concentration of H+, because these weak acids are not ionizing or dissociating fully, we cannot do that. So we have to use the equilibrium expressions to figure this out. So this is going to be very similar to what we did in our last unit, where we were looking at calculating equilibrium concentrations of a certain substance based on having 3 of the other 4 values. So when I look at this particular problem, I have HCN, which would be aqueous, reacting with the H2O as a liquid. It is going to form the H3O plus and the Cn minus, both of which are aqueous. So when I set this up, I initially have 0.200 molar for the HCN. At the beginning, I'm going to set up a rice table here. I would have 0 and 0 initially for H3O plus and Cn minus. I do realize with the water that there is the 10 to the minus 7th for the H3O plus, but it's so small it's not going to make a difference. So in this case, I know that my reaction would have to shift to the right, which means at equilibrium, I would have 0.20 minus whatever x happens to be. I have x here and x here. Now, just understand, in the higher realms of chemistry, you would deal with actually having to use the quadratic equation and plug in these values. But for us, we're just going to make the assumption that x is really small, and so it's going to be much smaller than that 0.20. So we're going to essentially say that the x is approximately 0 for its value for this. It is still important over here on the product side because we didn't start with any. But if I'm taking 0.2 and I'm subtracting 1 times 10 to the minus 5th, that's still going to leave me with 0.19999, which is essentially the same thing as 0.20. So it's just not worth doing all the math to figure that out. So from our little chart over here, in one of the previous problems that we had, You can see at 25 degrees Celsius, the HCN is equivalent to 4.9 times 10 to the minus 10th for its Ka value. So I would set up my expression H3O plus times Cn minus over HCN. Now I would have 4.9 times 10 to the minus 10th equals, I can place the x for each one, so I'd have x squared, x and x. I have the 0.20 here, so I can now solve by simply multiplying this out. So I have 4.9 second e negative 10 multiplied by 0.2 to get the 0.2 out of the denominator. That gives me x squared equaling 9.8 times 10 to the minus 11th. So if I take the square root of that answer, I end up with my x value equaling 9.9 times 10 to the negative 6. So that is my H3O plus, and it's also my Cn minus concentration. So now that I have H3O plus, all I have to do to solve for the pH is simply take the negative log of my answer, and you end up with a pH 5.00 in this case. So now let's look at an example where we're actually trying to solve for the Ka of an acid based on its pH. So if we used a pH meter and determined what the pH is, remember, we know that 10 to the negative pH equals the H3O plus. So if we set up our expression, and I have formic acid. If you guys aren't familiar with formic acid, if you've ever been stung by an insect, like an ant, they inject formic acid into you. So you would have H3O plus and HCOO minus, the formate ion. So as I look at this here, I'm going to again set up a Rice table to solve this problem. Except it's going to be a little bit easier because now my initial concentration, I have 10. So when I take 10 to the negative pH, I have 10 to the negative 2.38. So if I take second log negative 2.38, I end up with a concentration of 0.00417. So I know initially I had 0 for each of these. This was a minus x, this was a plus x. So now I know what my x value is because at equilibrium I have 0.00417. So if I take and subtract off the 0.00417 from my 0.1 initially, that gives me 0.0958 as my concentration of the HCOOH. In this case, because we already have the value, we can go ahead and plug it in to our expression. So now to solve for Ka, I would take the 0.00417 because that is my H plus. Let me set up the equilibrium expression here real quick. I'd have H3O plus times the HCOO minus all over HCOOH. So I take the 0.00417 times 0.00417, and we would divide it by 0.0958. So if we do that, we end up with a Ka value equal to 1.8 times 10 to the minus 4th. Again, since the 2.38, the 0.38 has two significant figures, as does the 0.10. I'm going to round this so I have two significant figures. The K value still is unitless, So my final answer, 1.8 times 10 to the minus fourth. So we're now going to look at using the KB to calculate the pH. Please remember, KB is talking about the base dissociating. So that's going to be producing OH minus in solution. So remember, to get to pH from the OH minus, we'd have to solve for POH and then eventually convert it to pH. So when we look at this expression, now we have NH3 in solution. Since it's a base, water is going to act as an acid. So I'd have the NH3 aqueous plus the H2O forming NH4+. The water is now giving away its hydrogen to the NH3, and I'll be left with OH minus. The KB expression would be NH4 plus the OH minus, my two products, divided by the concentration of my reactant, NH3. The H2O, just like in the previous example, is calculated into the KB value. For ammonia, our value for the KB is 1.8 times 10 to the minus fifth power. So when we look at this one here, we would simply plug in our Rice table values. I have NH3 plus H2O forming NH4 plus OH minus. For my I value, I have 0.15 molar. I would have minus X. On the product side, I'd start initially with 0 for each, but I'd be adding X. So at equilibrium, I'd have 0.15 minus X, X, and X. So now, setting that into our expression, I'd have 1.8 times 10 to the minus fifth equals X squared over 0.15 minus X. But once again, we're going to make the assumption that X is approximately 0, and so that will cut off the minus X portion. So I could now take 1.8 times 10 to the minus fifth, multiply it by 0.15 on each side, and that would give us 2.7 times 10 to the minus sixth equals X squared. So now take the square root, 2.7 second E negative 6, and we should get somewhere roughly around 1.6 times 10 to the minus third molar as my X value. But again, that is for OH minus. So I'm going to do it the easy way. Take POH being the negative log of the OH minus concentration. And if I take the negative log of 1.6 times 10 to the minus third power, we end up with a POH equal to 2.78. So now 14 minus 2.78 will equal the pH. So that should leave me with 11.22. We're now going to focus on the reactions between acids and bases and use the information of a known concentration to calculate the concentration of an unknown. This titration is simply a laboratory technique that we use to solve stoichiometry problems. The first thing I just want to stress to you is that an acid-base titration is nothing more than a limiting reactant problem. So when we look at the titration setup, our laboratory technique, we have a couple of vocabulary terms that we need to introduce to you guys to help you figure it out. So the first thing, the actual device that is holding the known concentration is called a burette. That known concentration that we are discussing, that is called the titrant. So I would have my titrant in the burette, and we're going to be analyzing an unknown concentration. So this would be our unknown down here. And it would also have the indicator. If you remember, the indicator was that weak acid system that was sensitive to pH and changed colors. We'd have the indicator down here in the bottom with the unknown acid or base, and this is called the analyte. Now, the whole purpose, as I said, is to neutralize the acid or the base with the other component. So we have something that we call the equivalence point. The equivalence point is when my moles of the acid, or the moles of the H plus or H3O plus, are equal to the moles of our base, which would be your OH minus, and it can also be equal to the moles of the salt based on the stoichiometry of the reaction. So equivalence point, that's the most important part of our reaction, because that's going to be when I have the perfect amounts of acid and base, so I have no limiting reactants involved in it. It's before we have the reaction finish and after the reaction has had the unknown neutralized. That's when we have our limiting reactant problems. The last thing, we have an end point. The end point occurs when the indicator changes color. And when we're talking about points, we're talking about volumes that have been added of the known substance. So the indicator should be chosen so that it's going to change its color as close to the equivalence point as possible. So now let's get into the mathematical formulas that we can use for titrations. So number one, you could simply use stoichiometry. If you want to set it up, get your rice table set up and go from there, you're perfectly welcome to do it. A little bit faster way to do it is this second formula, where we take the number of hydrogen atoms per acid molecule, multiply it by the molarity and the volume of the acid, and then that will equal the molarity of the base times the volume of the base times the number of OH minus ions per molecule. The reason we can do this is, if you recall our formula for molarity, we had molarity equaling the moles of solute divided by the liters of the solution. So when we look at this problem, the molarity times the volume, this is going to be equal to the moles of acid. And then the MB times VB, that would be equal to our moles of the base. This last component, the moles of the hydrogens or the hydroxides, that's essentially used in essence to balance the equation. And I'll show you how that works here in just a moment. So we're going to start this first problem off. It says for the titration of perchloric acid, HClO4 with potassium hydroxide, KOH, how many moles of potassium hydroxide will be required to react with 1 liter of 0.5 molar perchloric acid to reach the end point? So as we begin this process, the first thing we have to notice is I have a volume and a molarity for the acid. I'm not given anything for the base, so this is not a standard titration type of problem. It's just asking us to figure out how many moles would be required. So I need to set up my equation. So I have HClO4 and I have KOH. It would form the salt KClO4 and water. So this is already balanced as is. That's the important part of this. Because I have a 1-to-1 ratio, I know when I calculate my moles of acid, that's going to equal the moles of the base. So I can simply take the 0.500 molar equals X moles of the HClO4 over 1.00 liters. So that would give me 0.500 moles of the HClO4, which means I would have 0.500 moles of the KOH. From a stoichiometry standpoint, I could start off by just saying I have 1 liter of the solution, 1 liter, 0.500 moles of the HClO4, and then I could use my mole ratio. For every 1 mole, of the HClO4. There's 1 mole of KOH, so I'd have 0.500 moles KOH. We're now going to do a problem using the titration formula. I'm going to use both methods just so you can see how the numbers work out to be the same thing. So for this example number 2, we're determining the solution concentration by an acid-base titration. It says one commercial method used to peel potatoes is to soak them in a sodium hydroxide solution for a short time and then remove the potatoes and spray off the peel. The NaOH concentration is normally 3 to 6 molar and the solution must be analyzed periodically. In one such analysis, 45.7 milliliters of 0.500 molar H2SO4 is required to neutralize 20 milliliters of the NaOH solution. What is the concentration of the NaOH solution? So I'm going to start off using the stoichiometric method, what you've done traditionally up until now. So I've got to balance my equation first. So I have NaOH plus H2SO4. It's going to form Na2SO4 and H2O. When we balance it, I'd have a 2 for the coefficient of NaOH and for H2O, so we're all set and ready to go. So for this problem, I'm going to start. I have the 45.7 milliliters of the H2SO4. I'm going to convert that into liters, so 1,000 milliliters of the H2SO4, 1 liter of the H2SO4, and now I can use my molarity, so I know for every 1 liter of H2SO4 I have 0.500 moles of H2SO4, and now I need to convert that into moles of sodium hydroxide. So when I do that, for every 1 mole of H2SO4 we need 2 moles of NaOH. So when I set my math up and I divide 45.7 by 1,000 and then multiply that by 0.5 and multiply it by 2, we end up with 0.0457 moles of NaOH. And we need to divide that by the 20 milliliters, which would be 0.020 liters. And when we do that, we have the molarity equaling 2.28 or 2.29. Okay, so I get 2.29 molar for the first problem using that method, and now I can go on to my second method. So I have my number of H plus ions per molecule multiplied by the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base times the number of OH minus ions. Okay, so I have 2 hydrogens, again the H2SO4, 2 hydrogens times the molarity, 0.500 molar. It's nice with this formula because you don't have to convert between milliliters and liters because they'll cancel off. So I have 2 times 0.5 times 45.7, and that's going to equal the molarity of the base times 20 milliliters times 1 for my number of hydroxides. NaOH, 1 molecule has 1 OH minus molecule. So when I take this, 2 times 0.5, that would be 1. So I'd have 45.7 divided by 20. So the molarity of my base would still come out to be approximately 2.29 molar NaOH. So either way, you get the same answer. It's just that second method is a lot easier to use. But I just wanted you to understand, if you notice over here, I'm taking the molarity times the volume. Notice here I have volume and I have the molarity for the H2SO4, and then I multiply it by 2. Notice my coefficient for the sodium hydroxide is A2. So I have in the numerator 45.7 multiplied by 0.5 multiplied by 2, 2.5, 45.7. Then once I have my moles, I would divide it by the volume of the base. Notice here, I'm taking and dividing both sides by the volume of the base. So I'm doing the exact same process, it's just making it a little bit quicker to work through. Okay, so this is our last example problem set. So after this, you are officially done. Congratulations. So the first question says, what is the molarity of an HCl solution if 27.3 milliliters of it neutralizes 134.5 milliliters of a 0.0165 molar BaOH2 solution? So again, I'm going to take for this one, I have 1 for my number of hydrogen ions. I have the Ma times 27.3 milliliters, and that's going to be equal to 0.0165 for the molarity times 134.5 milliliters. And this time again, my hydroxides, I now have 2 for that. So if I take 0.0165 times 134.5 times 2, and then divide that by 27.3, we end up with the molarity of the acid equaling 0.163 molar. So our answer for that would be C. For our last problem, what is the molarity of NaOH solution if 48 milliliters neutralizes 35 milliliters of 0.144 molar H2SO4? So for this problem, again, we can take the 2 for the number of hydrogen ions in the sulfuric acid. We have the initial molarity, 0.144, and we have 35.0 milliliters. And that's equal to the base molarity times 48 milliliters times 1 for my number of hydroxides per molecule. So if I take 0.144 times 2 times 35 and then divide that by 48, we end up with the molarity of our base equaling 0.21 molar, 0.210. All right, so that concludes everything for our acids and bases. We would typically talk about some titration curves, but I'm going to limit it at that so I don't run over for time. So thank you guys. I've enjoyed having you in class this year. Unfortunately, won't be seeing each other face to face again, but please stop by and say hello next year.